All right, so we figured out the 12 different symmetry operations for D3d. And so now that we have those and they're organized into classes, um, well, we know that the very first irreducible representation is always going to be the totally symmetric one with ones across the board. So it's going to be 1, 1, 1, 1, 1, 1, 1. And then we know that there are 6 different classes, so that means we're going to have 6 different irreducible representations that we're going to find. So we're going to do this in a very similar way that we did with the C2V character table. We're going to pick a vector, and this time I picked the Z vector to get us started. And so we do the identity on Z. Z goes to Z. That's going to give us a 1. If we do a C3, well, we're doing a C3Z, right? We're doing the principal rotation axis is a Z. So we're just rotating this Z vector. So that's not going to change, right? We're not flipping the vector or anything. We're actually rotating in this way, and the Z vector is here. So we're not changing that. So Z goes to Z, the character is going to be 1. A C2, though, that's perpendicular to the Z, so that's going to be 180 degrees, and Z is going to go to minus C. So that's going to be negative 1. Inversion, X, Y, Z goes to negative X, negative Y, negative Z. So by definition, Z goes to negative Z. That's going to be negative 1. And an S6. An S6, we're doing a C6, rotating it. That does nothing to the Z vector, but then we're going to be flipping it with a sigma H. That turns it into negative Z. So overall, Z1 to negative Z, character of negative 1 right there. And then sigma D, those are in the plane that contains Z, so that's not going to do anything, so we get a 1. So that's how we get an X character. So now we're going to do the same thing with an X vector. And what you'll quickly see is that something a little more complicated happens here. And so and this will really drive home, hopefully, this example of where the characters come from and connect a lot of the topics we've been talking about so far in the course. So let's try to do this. So first, if we do X, we'd say, okay, X goes to X. We're going to do X vector, and we're going to do identity. X goes to X. Fine. Now, what happens if we do C3? Well, if we have an X vector, right, and we're doing a C3, there's our X vector, we're doing a C3 around the Z, that's the principal rotation axis, and we're going to rotate this 120 degrees. And so what is going to happen? Let's say we rotate it this way. You're not going to get anything that's clean. It's not going to be negative Y, negative X, anything like that. You're going to get something like this, right? It's going to be 30 degrees off from the Y, because we're doing 120 degrees, right? And X and Y are 90 degrees apart. So this gets complicated. And we have to go back to our transformation matrices that we learned previously for angles, okay? And so this was a formula that I gave to you. This was back in chapter 1, right? For a rotation along the Z, you're going to have a cosine of the angle, sine of the angle, negative sine, and cosine of the angle. And that's going to be a 2x2 matrix. And so really what this is telling you is that X is going into some linear combination of X and Y. So we could call that AX plus BY. You know, we had an X vector here, and X went into AX plus BY. And similarly, if we had a Y vector, you can imagine how that would also go into some other linear combinations, CX, let's call it, plus DY, right? And what are those coefficients? They're given by this transformation matrix here. And so in other words, X and Y are dependent on one another. The X vector doesn't go cleanly into itself or the negative of itself. It goes into a combination of itself and Y. And similarly, the Y vector goes into a combination of itself and X. And what we call this is that X and Y transform together. And because of that, we can't break up these matrices any further. Before we were, essentially when we said, you know, Z goes to negative z. Essentially what we're saying there is we are saying that z times -1, a matrix, a 1 by 1 matrix, went to negative z, right? I guess I can make this a matrix too. And we could break this up because z transformed independently. This came from block matrix multiplication, actually. We had zeros on the off diagonal. And in this element we do, right? In this, we could break this up. For E, we could break it up into two 1 by 1 matrices because we have these zeros that are off diagonal. That's our block matrix multiplication we started the chapter with. So for identity, we could break it up because X just goes to X. It just goes into itself, and Y just goes into Y. But for C3, X and Y go into combinations of each other, and you have non-zero elements on the diagonals, okay? And so this is where you need to remember a little bit of trigonometry, because what we're going to be doing is taking the trace of these matrices to figure out the character. So here, now that we know that X and Y transform into one another, we're going to keep them as 2 by 2 matrices. So we take the trace, right? So the trace of the matrix is 1 plus 1. It's a sum of the main diagonal. And so the character here is 2. So that's why we have a 2 right here under E. Here, the character is going to be cosine 120 plus cosine 120. Again, it's just the trace. And you're going to have to remember your trigonometry here, your unit circle trigonometry. Luckily, there's only so many. But cosine of 120 is -1/2. So essentially, you have -1/2 plus -1/2. That gives you -1. And that gives you your answer. If you get a fraction or some weird number, you know that you did something wrong, either in setting up your matrix or something like that, or you got your trig wrong. So the fact that even though we had fractions, -1/2, -1/2, but then we ended up with the trace being a nice whole integer, that is a good sign. So that's -1. So now we're going to do C2. And so, yeah, there's on all these matrices, I didn't write it, but there's, you're asking, what does the point x, y do? So you're doing x and y, okay? So again, we're gonna have a 2 by 2 matrix for C2. C2 is a perpendicular C2. Which C2 do you choose? There's 3 C2s, right? It doesn't matter. Which C3 do you choose? It doesn't matter. You could have done the C3-2. We did the C3-1, the C3. That's 120 degrees. But if you did the C3-2, you'd have 240 degrees here. You'd still get a trace of -1. You still get the same character, okay? And same with the C2s. This is the cool thing about symmetry elements being in the same class. They'll always have the same character. That's a property of them. So it doesn't matter which one you choose. You just need to choose one of them. So we have 3 different C2s we can choose from. I chose one where I just defined the x. I defined it along. Let me clear some of this here. So I defined it as going along the y. So I actually defined it as this rotation going along the y. Okay. So we're doing a 120-degree rotation along that. So this hydrogen is going to go to that hydrogen. But if I do that and I'm rotating along the y, y is going to go to y. And x is going to rotate around and go to -x, right? If I have an x vector here, that's going to go to -x. So that's what this is saying. A -1 there, x is going to -x. This is a 2 by 2 matrix that says x goes to -x and y goes to y. Add the trace up, -1 plus 1, you get 0. This is a two-dimensional matrix that is much more complicated, right? And we could figure out what it is. It's going to be x. We don't really care because we only care about the trace, but just to show you, right, what is this going to be? Again, this is times xy, right? So we're saying that x is going to turn into cosine of 120 times x, right? This is just row by column matrix multiplication. And then plus the sine 120 times y. Well, what's sine of 120? That is √3/2. So we're saying, again, these are, now we're figuring out our coefficients of these a's and b coefficients I was telling you about before. X and y are transforming together. But again, we don't really care about this value. You don't even have to evaluate. We just evaluate that. We don't care about it because what we care about is the ones on the diagonal, right? So you don't even have to do that math. Keep going. Inversion. Inversion takes x, y, z to negative x, negative y, negative z. We know x and y transform together, so we have to keep it as a 2 by 2 matrix still. X is going to go to negative x, so we put a -1 there. Y is going to go to negative y, so we put a -1 there. We get -2. C6, sorry, S6. S6, we're going to do a C6 and then flip it across the z. But we don't care about the z, right? Because the z is the sigma h part. We don't care about the z. We're only doing x and y. So it becomes just a 60-degree rotation. Cosine of 60 degrees is 1/2. And so you're going to have 1/2 plus 1/2 along your trace there, gives you 1. Okay, again, your trace. So that's a character of 1. That gives you this 1 here under the C6, S6. And then your sigma d is the last one. Again, I'm just going to define it as going through the same little area, the y. And let's see. No, actually, this time I defined it differently. I defined it as going through the x. These are both sigma d's. They'll get you the same answer. So if you define it as this one right here, x doesn't change. It contains the x vector, so you have a 1 here, and y would change. You have a -1 there. If you did this other plane here, you'd have a -1 here and a 1 there. But in both cases, you have a 1, 1 and one -1. You add those up to get your trace, you get a 0. And so that's why you have a 0 here. So that was all just trying to figure out this one, character here. So that's what happens. Sometimes this is an example of a irreducible representation with a dimensionality of 2. And what that means is that two functions transform together. They transform into linear combinations of each other. So this is a big point. It's a really key point. It's a point that you don't learn about, at least I never have seen an undergraduate course that teaches this because it takes some math, right? But you always learn, if you have learned character tables in your undergraduate course, you learn about just ones and -1s. Well, how do you get a 0? How do you get a 2? This explains it. It's when functions are transforming into one another that you get these odd situations, okay? So we'll keep going on this one in the next video.